Welcome. This is a Z Academy, a place where you can learn about topics in machine learning, deep learning, and artificial intelligence. How to convert sketches into color images using deep learning. If you have followed our previous lessons, you would be familiar with latent spaces and GANs. If not, you can check out our earlier lessons on these topics. In this lesson, you will learn about conditional GAN architecture. You will also be able to build one from scratch. After that, you will be able to apply the CGAN model on a fashion products data set for converting sketches of products into color images. Conditional generative adversarial network. If we would like to generate one set of images while giving a different set of images as an input to a GAN model, this problem is called image translation. A classic GAN architecture does not take into account class labels, therefore we require a modified version of GAN. A GAN architecture, which generates a certain type of images dependent on the type of a given class label, is called a conditional GAN. An example of a CGAN is given in this figure. As with a classical GAN, it has two main networks, a generator network and a discriminator network. However, the generator is a symmetric network, similar to an autoencoder which takes an input class condition, for example, a sketch image, as an input and returns a color image of the product as an output. The discriminator is similar to a typical GAN architecture. However, a grid of output decisions is created instead of having a single binary output. This helps in computing the better fine-grained loss between real and the generated images. The discriminator takes a condition image, for example, a sketch image, and the real image as an input, and compares it against the generated output from the generator. The output of the discriminator is a grid of decisions about whether the image is real or a fake image. Let's look at the loss function computation. As with the GAN, the CGAN has two losses, a generator loss and a discriminator loss. Both of these form the objective function for the optimization. The generator loss has two components, an L1 loss and the output of the discriminator. The L1 loss is computed by taking the L1 distance between input condition image and the output of the generator. The two loss values are linearly added together in order to compute the generator loss. The discriminator loss consists of two terms as well, a loss on the real image and the loss on the generated image. The real loss is the discrepancy between the real images and the decision of the discriminator, while the generated loss is computed by the decision of the discriminator using the generated image. Pause the video and see if you understand these losses and how they relate to each other. Implementation. We will use an open-source data set of fashion products, which we have used in our earlier lessons as well. However, since the data set doesn't have any sketch image, we shall have to prepare the data set first in order to generate a set of image condition pairs. Luckily, creating sketches digitally from given color images is a simple image processing task and can be accomplished with a few lines of code. We shall pre-process each image in the data set and generate a set of joint sketch and color image pairs. The output result of a new data set after such a pre-processing can be visualized in this figure. Now let's build the model. We will construct a CGAN model in this section. As explained earlier, a CGAN consists of two sections, a generator network and a discriminator network. We shall build both consecutively. As can be seen from the figure, in the first half of the network, each middle layer block of the network consists of three layers, that is, a 2D convolution layer, a batch normalization layer, and a leaky relu activation function. These blocks are repeated until latent dimension, Z, is achieved. The second half is the mirror of the first half of the network. The autoencoder architecture provides a compress-to-compress framework, whereby encoder compresses the redundant data in higher dimensions to a lower dimensional space, while a decoder recovers the data from the compressed latent vector. We shall also use a U-Net architecture in this construction, which is a special type of network architecture that is used for image segmentation tasks. In a U-Net architecture, each convolution layer block on both sides of the symmetric network is connected using skip connections. This allows the decoder layers to receive input from the encoding part of the network. As we saw earlier, generator network consists of block of layers. It can be implemented by creating a custom layer function, as shown here in this code snippet. Generator is an autoencoder architecture which contains two subnetworks, an encoder and a decoder. This means we have to create a custom layer function, one for downsampling and one for upsampling. Each downsampling function contains a set of layers, a convolution layer, a batch normalization layer, and a leaky rel layer. Same as the downsampling, the upsampling layer also has a set of layers, a deconvolution layer, and a relu activation function layer. There is also a dropout layer in the upsampling block of layers in order to perform regularization. We use the downsampling layers and the upsampling layers functions in order to create layer stacks. More specifically, we create to Python lists a downstack layer stack and an upstack. A set of 7 custom layer blocks are added by calling the custom downsampling function 7 times. Note here that the image size reduces to half after each layer block. An upstack consists of 6 upsampling layer blocks which are added by calling the upsampling layer function 6 times. While we are creating the encoder network, we also prepare a Python list called skip, which is initially populated by the layers of the network. Then the order of the items in the skip list is reversed. This allows us to have a one-to-one mapping with the decoder layers. We use this skip list for creating skip connections when we create the decoder network. Pause the video and see if you understand the code and how the network is constructed. The discriminator is constructed in the similar way as the generator, however, the layers are different. A discriminator is a classification network which takes a color image and a condition image as an input and outputs a grid of probability values. Therefore, an input layer of the network is a set of 2 images of size 128 by 128 by 3, and output layer is a 32 by 32 grid of probability values ranging between 0 and 1. These probabilities tell whether the input pair is real or fake. The construction of the discriminator network is shown in this figure. Just like the generator, the middle layers consists of blocks of layers. Each middle layer block has a 2D convolution layer, a batch normalization layer, and a leaky relu activation function layer. The number of middle blocks depend on the size of the image and are repeated until image reached a small enough size, for example, 32 by 32, which is the set of output probabilities. Discriminator only has downsampling layers. Each downsampling block of layers is constructed by this custom layer function. It adds a 2D convolution layer, a batch normalization layer, and a leaky rel layer. Each call to this function returns a bundle of layers. The make discriminator function constructs the complete discriminator network. It first adds 2 image inputs, one for the color image and one for the sketch image. Then it adds 2 downsampling blocks by calling the custom downsampling function twice. It follows a convolution layer without downsampling. In order to control the output size, a 0 padding layer is added before the convolution layer. The convolution layer is followed by a batch normalization layer and a leaky rel layer. A final 2D convolution layer is added to get the output. A sigmoid activation can be used here as well. However, it isn't necessary because we only need this output for the computation of error, and these values are normalized. Now let's train the model. As with the GAN, the training of the conditional GAN consists of individual trainings of both the discriminator and the generator. For each training step, we train the discriminator network on real images with labels and the fake images obtained from the generator network. The labels or the conditions for the real images and the fake images are fed to the discriminator network, and loss for the real and the generated images is computed. In this way, although generator and discriminator network are being trained separately, their losses have been constructed in such a way that they depend on the output of each other. Let's look at the results now. A sample output of the trained generator on fashion product sketches and color images is shown in this figure. Since there are multiple classes of objects in the data set, we can train a separate model for each item. You can also train a single model for all items, however. Network construction has to be changed. We chose a simple construction for the purpose of this lesson. We can do the same with other items as well. For example, here are the dresses being converted from sketches to color images. And here are the sketches of the shoes being converted to color images. And here are the sketches of the watches being converted to the color images. And here are the sketches of the handbags being converted to the color images. This concludes the lesson. You should have learned by now how to construct a conditional GAN, how to use a conditional GAN to perform image translation, how to convert sketches into color images. Thanks for watching the video. I hope that you have learned the concepts in this video and it would improve your understanding and knowledge. Feel free to post your question in the comment section below. If you find this content useful, please like, share, and subscribe to the channel.